we are going to go to University of Nevada at Reno. We have two presentations from there. The first one is on numerical investigation of the impact of vertical ground motions on the ABC girder-to-cap connection in near field. Dr. Muhammad Mustafa is going to present it on behalf of Dr. FLORIANA PETRONE. Dr. Mustafa?
Right. Thanks a lot, Dr. Mehrabi. It's always great, to be presenting for the research days. So I just wanted to first convey, Dr. Petrone's apologies. She is actually participating in another Department of Energy meeting, so she couldn't unfortunately present. So I will be presenting on her behalf. So this project, Dr. Petrone, what she's looking at, she's an expert actually in earthquake engineering, and her expertise is mostly in regional simulation and large scale, applications of earthquake engineering and different ground motion, the effects and the impact of ground motions on the response and of our structures. So she has a very I would say unique expertise in seismology and earthquake engineering from a structural engineering perspective. So one of the main things that motivated this project is that vertical ground motion, specifically for those who are familiar with the seismic world. Basically, earthquake engineering, what we have been traditionally doing in many of our codes and everything, we usually use the horizontal components of ground motions, and although the codes are aware of the vertical component as well, none of really the analyses or the design are comprehensive enough to account for the effect of the vertical ground motion. So when we were talking about this project in the, a few years ago, what Dr. Petrone was envisioning is that some of the ABC connections might be specifically vulnerable for the vertical component, unlike the traditional horizontal or the traditional earthquake analysis that we do. So maybe some of the connections can have maybe extra tension forces, some uplift risks, and that's why the motivation for this project was to incorporate the vertical ground motion effects in the design, or basically assessment first of the ABC connections. So to do this, the objective basically is to look at the effect with and without the ground motion. So everything is done in this project comparatively. So as you will see when I show the results that they have developed, they have looked at the effect of the ground motion with and without the vertical component to see if it's really worth it to have some recommendation or design recommendation to incorporate the vertical component or not. If it is found to be negligible, then that's great. If not, then there should be something to do about it. To do this, you will need a lot of analysis. So this project is purely numerical. It's easy to do, experiments with 3 components. We have several shake tables around the country. Here at UNR, we have one that we can use for 3D earthquake simulation. But the catch is that you cannot really get to do anything meaningful at a large scale for these things, because many of the shake tables, for those who are familiar with seismic testing, you need to have masses to, simulate basically the similitude and the actual, even when you reduce scale. So when you have a bridge, the column basically is getting a lot of mass from the superstructure of the bridge. So even though we might do a shake table test for a column only, you will see this in the next presentation when I present my project, we still need a lot of additional mass to represent the superstructure effect. So when we do vertical excitation, this is usually from the equipment perspective, the shake table itself, the actuators in the vertical direction do not have the capacities to do this. So it is important to have experimental testing, and I'm a big fan of experimental testing in general, but in some cases you cannot really do a lot about it. And if we talk about this specific project, there isn't really that much that you can do with experiments, because even if you have a shake table that can be used to simulate the vertical component, then you have to do different connections, different ground motions. There is ground motion variability, so it becomes very, very unfeasible. So that's why it is important to do this numerically. The reason I'm also spending some time to talk about the challenges of doing this experimentally is that if we were to do this numerically, now you have to do things even the numerical case, it's not as simple as you might expect, because at some point you might have a component and you start doing some detailed modeling for the ABC connections. But if you were to extend this to the design level and start talking about design recommendation, we need full prototypes, full bridges with different connections and different components, and we need to do dynamic analysis, time history analysis, nonlinear, of course, and you need to use different suites of ground motion. So even from a numerical perspective, that's a very challenging project, or a challenging problem to address. With this said, why I'm saying all this, to get to a specific point, and the main objective is, or one of the side objectives of this project, which is very important from what I can see even as an external viewer of this project, is that how to validate or develop and validate reduced order models of typical ABC connections. That's not a trivial task. In the easiest way, we can just assume ABC connections can just behave as cast in place construction and have the columns and beams together, without any specific ABC connection. But if you do this, you are not really capturing any local stresses within the connection. You are not really capturing, if you are talking about the vertical component effect as well of earthquakes, you will never be able to see this from your analysis. So the goal of this project is to, not only to understand the effect of the ground motions, the vertical component, but, parallel to this, they are developing detailed models and using these detailed models to create a simplified reduced order model that can later on be expanded at the full bridge component. So that's, again, this is not a trivial task by any means. And I have been working with ABC connections and experimental earthquake engineering for the last 10, 15 years. And I can tell that this is a very challenging task. So some of the results that I'm showing that, Dr. PETRONE sent us to share with you today are really, new and unique in this sense. So what they wanted to do in this project, like Dr. PETRONE and her PhD student, they wanted to do a literature review first to pick. We have so many options for seismic ABC connection. Which ones, are more likely to, or which one are the more, the more common one, the more popular one, the easier at least to start with in terms of modeling. So the first task is just to shortlist the connections and pick one. Then second task is to build a micro model, 3D finite element nonlinear model using one of the general packages software, and then use the results from the micro model to develop a reduced order model. And once you have a reduced order model, you can just extend this to a full bridge. Then in this case, you can use applications or like software like OpenSeas. These are much, much faster. They are well suited to do system analysis for the structure, the full structure or the full bridge. They can do a lot of dynamic history analysis. You can do a lot of suites of ground motion. Things are more suited in OpenSeas, for example, to do hundreds of ground motions, unlike if you were to do it in ANSYS or Abacus or something like that. So transitioning from a micro model to a reduced order model is of a paramount importance for this project. Then, they will identify a statistically significant suite of array, like near field motions. Again, for those who comes from the seismic world, you might know, or you might recall that the effect of the vertical component is only, highlighted in the near field motions. If you are far field or far from the source of the earthquake, the vertical motion, has high frequencies, and they are tended to be even to arrive. The nature of the seismic waves that generate the vertical component, they arrive few seconds even earlier than the horizontal component. So when you see the ground motions that I will show in one of the slides, you will see that there is a shift between the peak of the vertical ground motion and the horizontal ground motion. So these, to be accounted for, you need also a statistically significant suite of arrays, which you will never be able to analyze and get comprehensive results unless you have a reduced order model. And all these things will be eventually, provided in some sort of simplified measures to advance the current design methods in the capacity design. So in the framework of the capacity design. So that's what you see underlined here is the objective of this project. So in terms of the first task, the identification of the connection. This is what you see here is, again, they did a lot of literature review, but this is just a final selection that they have made. They focused on precast bend cap systems. They focused on non-integral bend caps, although there is an integral bend cap for those who are familiar with Caltrans, bridges. 90% of their bridges use the integral bend cap system, and that is in high seismicity. So they are looking into this as well, but this will be a second phase, or maybe in a future project or so. For this project, they are starting with the non-integral bend caps that is more suited for low to moderate seismicity. They are looking at the emulative, where you can just cap a width, connection where you just have the precast column and the precast bend cap, and you just have the pocket inside the the bend cap, where you just plug in the column, and then you either have the column reinforcement only sticking out, and then you fill the joint or the pocket with wet concrete. That's why, you know, like, or there is a dry version of it as well. But what they are looking at here is the wet, you know, like cap pocket connection between columns and bent caps. So this is the selected, you know, like connection. Now that they have selected this connection, what they wanted to do? They wanted to just get some typical, you know, like the dimensions, designs, reinforcement in the columns, you know, some diameter, like how much reinforcement in the cap beam in the column, the connection reinforcement, and so on. So they went through some, you know, like archetype, bridge archetypes, and they used it to generate their specimens, if you will, the new specimens that you will use for the micro modeling before they expanded it to the reduced order model. So this slide just shows the details, and you will be provided with a copy of the PDF, so later on the audience can take a careful look at the dimensions and so on. This is also some, you know, like schematics that show what you have seen in the previous slide, the final dimensions that they have used, and how did they come up with these, you know, like specimens. These are, again, the numerical specimens. In the lab, we do, you know, like physical specimens. In the finite element world, they do numerical specimens. So that's a numerical specimen. The only difference between numerical and physical specimen is that you don't really need to do reduction in your scale. So you can see here that this is a full scale, at the full scale of the bridge. So the column is an actual, you know, like 4-foot column. The representative part of the cap beam and the depth of the cap beam, all these are the actual dimensions. It's just a sub-assembly. It's just a part of the bridge, and this is the different reinforcement that they used for their design. So what they did before they went, you know, like to model the ABC connection, they just wanted to calibrate some models. So the software that they used for this is Diana, FEA. That's finite element analysis, you know, like package from Netherlands. So Diana, they used it for just some very, you know, like simple cast in place columns that was tested under pushover analysis. I mean, that was a push through failure. So it has the full nonlinear behavior of concrete, including all different, you know, like regimes of failure, like concrete spalling, core damage, and reinforcement, and so on. So they just calibrated their model. They had some confidence that they can model concrete in 3D, and they proceeded further to the ABC connection. So the second task is to focus on the micro model in Diana for the ABC connection, and this is some pictures that you see here. Again, the bent cap, a column, and the connection between the bent cap and the column. There is a corrugated steel pipe that they have used. There is grout. So there are multiple materials here that they have. And this is the details. Again, there is no need to go over the specifics here. There is a concrete model. There is a grout model. There is a corrugated steel pipe. There is the bone slip to account for the friction between the different materials at the different layers. So these are the final parameters that was used for defining the material models in the Diana. These are some of the results. They did, first of all, before they went to look at the effect of the vertical motion, they just did a simple like pushover analysis. And the pushover analysis that you can see here, just to get an idea where the failure happens, the grout cracks, the failure happens at the, like interface, if it were to happen, or it happens in the column and you develop the full plastic hinge in the column as intended. So here they confirm that the connection survived, and they have, like the failure happens in the column as intended. That's a double curvature column, as you can see. So you develop two plastic hinges. So at least they had some like initial confidence in the ABC connection model, and then they went to do the dynamic analysis only for the sub-assembly. This is not a full bridge. This is just a column whose a sample or a representative part of the cap beam, as you have seen. So they did some dynamic analysis. Here, this is the plan view. If you were to look at the bridge from the top, this is, like the transverse direction, like in the longitudinal direction. So that's how the, like column will work. And they have done actually the vertical excitation as well. So this was excited one time under only horizontal components and another time under all three components. And they have, like characterized the peak displacements and so on. But what is more interesting is this, not this even slide, the next one. But here, what I mentioned a few minutes ago is that the nature of the earthquake itself, you can see here that the longitudinal and transverse and the vertical excitation, the frequency, and this is a huge, like difference. And this is how you can visually even, like detect the vertical component or distinguish it from the other components. You see here, it sounds like more noisy because you have higher frequencies. So the vertical excitation is of nature is having much higher frequency than the horizontal components. For instance, that's the response spectra that is equivalent to these vertical excitations as well. At low periods, they have very, very high peak ground acceleration or spectral acceleration. So that's why vertical acceleration, if it is, found to be like important to account, it is huge, as you can see here. So it is not something that you can trivially or just over like look or something like that. And that's the some of the results: transverse direction, longitudinal and vertical direction with and without the vertical component. So it's obviously that the transverse the analysis in the transverse direction is not as sensitive to the vertical component as would it be in the vertical direction. So whether you account for the vertical component of the earthquake or not, the bridge behavior in the transverse and longitudinal direction is almost the same. The overturning that's associated, like with the lateral components, the abutment, like effects later on, even from a bridge perspective, a full bridge perspective, it is even less and less, like expected to have any change in your longitudinal and transverse direction response because of the vertical component. Nevertheless, if you look at the vertical direction now, this is very dependent on the vertical component. So whether you have to account for the vertical component or not, you can see here you have almost 30%, like higher displacement that can be overlooked if you're not accounting for the vertical component. And more importantly, when it comes to the plastic and damage and the post, like earthquake residual displacement, we have 240% increase in the residual displacement in the vertical component. So this is again just like some more pictures. For the interest of time, let me get to the next task. What they wanted to do, they wanted to do a reduced order model in OpenSeas. As I said, the motivation for this is that they can extend it now to the full bridge. They can like do different prototypes of bridges, different ground motions, large suite of ground motions, and so on. So that's like some of the basic features of the reduced order model. The connection will be like modeled using some springs between the column and the beam. So the column and the beam here, what you see here, the yellow, like dots, this could be a precast column with a precast beam connection, and you can just have a whole bunch of springs at the local level here, which they are working on calibrating now. These springs, so there will be springs, of course, at the foundation level. There are springs for the abutment. These are well defined now, and the literature provides tons of information about these types of like connections. But when it comes to ABC connection at the local level, this is yet to be developed, and that's what Dr. Petrone is working on with her students. That's again some of the like model validation, but using the OpenSeas, not the Diana one. And they extended this to a full bridge model, as I said. So they are looking at the abutment as well. So these are all more details. So what they wanted to do, I think I need to end it here so that I can leave some time for questions. I think what's more important is to note again the big picture. The big picture here is that vertical components shouldn't be overlooked, like in some of the local ABC connections, especially if you are in the near fault, like in California, for example. This is something that needs to be accounted for. There is a good ongoing effort to produce and provide, like some modeling guidance, not only guidance on the design, but also on the modeling part, how to go for a reduced order model using OpenSeas or something similar at the local level that can account for the ABC connection physically using springs or so, not just the very crude assumption that we have been doing for decades or years, not decades, maybe for years, that we just model ABC connection as if it's cast in place, like connection, assuming they have comparable behavior. Now, this project will provide some guidance on doing local behavior and local modeling for ABC connections. And eventually, when they are done with this project, there will be some guidance on the effect of horizontal only versus horizontal and vertical earthquake response of ABC bridges. So I think Dr. Petrone has leveraged a couple other projects that she is doing, and she has a full PhD student dedicated to it. So the project is not completed yet, but I think along with the other projects, there will be a lot of good design guidance that will come out of this project. So with this, I would like to thank you and maybe answer a question or two.
Thank you very much, Dr. Mustafa. You presented even better than like it was your own project. But one quick question, we have like 30 seconds time. Would you also compare the behavior of monolithic connection with precast connection?
Oh, that's an excellent point, actually. That's an excellent question. I don't know if they are willing to do this, so I cannot answer on their behalf, but I can indeed, pass this question, Dr. Petrone. That's a very interesting, point. Since they will have all these great models at the micro level and at the macro level, why don't they look at the, monolithic versus ABC connection in this case? Yeah, that's an excellent point. I think I will pass this comment, but I'm sorry, I don't have an answer. I don't know if they are doing it or not.
Yes. Thank you. Thank you very much, Dr. Mustafa.